Okay, so this is the second video for lecture set 10. This video will just be about how to run a chi-square independence test. As I mentioned in the first video, the chi-square goodness of fit test is essentially the hypothesis test we use for a single qualitative variable. So if we are interested in determining if the outcomes of a single qualitative variable follow some pre-established distribution, that's a goodness of fit test. The chi-square independence test is a test that is applied to two qualitative variables. And effectively what we are asking is there a relationship between the outcomes in these two qualitative variables? So in this context, when we say relationship, we mean not independent, where independent has the same definition that it did earlier on in the course. All right, so for example, suppose that a manufacturer buys circuit card assemblies from two different vendors who we're calling A and B. All right, so these circuit cards can come with one of three types of nonconformity issues. So there can be no nonconformity issues, there can be minor nonconformity issues, or there can be major nonconformity issues. And the question is basically, are the vendor, so A, B, qualitative outcomes, and the type of nonconformity, none, minor, major, qualitative outcomes, are they related to each other? Is there an association between where we buy the card from and the type of nonconformity that we are dealing with? So you can see that the data for this type of experiment is in the form of a contingency table. Once again, we have two qualitative outcomes or two qualitative variables. We display counts between those two qualitative variables using contingency tables, just like we did back in lecture set 3. So anytime we see data in this setup, we should automatically start thinking chi-square goodness or chi-square independence test, because the independence test is the only test that applies to data that are displayed in a contingency table. Okay. Now the independence test is basically asking, are the variables associated with each other? So we are testing the null hypothesis that the variables are independent or not associated versus the alternative that they are not independent or are associated. So you can see that there are different ways that we can write these hypotheses. I think that because the test is called an independence test, it's fairly natural to use the first set. So the null hypothesis is that the variables are independent. And then the alternative would just be the opposing statement that they are not. But not associated and associated mean the same thing. Don't have a relationship, have a relationship. This could work as well. There are different ways of phrasing this, but the general idea is that we are testing for relationship between these two qualitative variables. All right, so just like the goodness of fit test, the independence test, well, just like any hypothesis test, the independence test is run in 6 steps and starts with an assumption check. These steps are identical to what we saw for the goodness of fit test. The only difference here is the null and alternative hypotheses that are given on step 1. So again, we can express this as the variables being independent versus not independent. I have written here not associated versus associated, but these all mean the same things. So there are different ways that we can express this, but the underlying question is the same. All right, now the key differences here are actually just going to be in how we compute capital E, the expected values, and the degree of freedom calculation that we use on step 4. So for an independence test, the degree of freedom calculation is the number of rows in the contingency table minus 1 times the number of columns in the contingency table minus 1. Exactly. Yeah, sorry, that's exactly right. So for example, we have 3 rows in our data set and 2 columns. So we'd have 3 minus 1 times 2 minus 1, which is 2 times 1, which is 2. So we have a different degree of freedom calculation. The expected value calculation is also unique. So what we do here is we take the row sum, we multiply by the column sum, and we divide by the sample size for the entire contingency table. So we have to do this for each entry within the table. For example, okay, so you can see here, if we wanted to find the expected value for row 1, column 1, we would take the row total for column 1, which is 537. We'd multiply by the column total, which is 418, and we divide by the sample size, which is 703, right? And then if we wanted to do this for row 1, column 2, it's the same pattern. Basically, we are just moving to the row total for whatever the entry is, dividing by the column total or multiplying by the column total for whatever the entry is, and then dividing by the sample size for whatever that entry is. And so that's the pattern that we are using throughout the calculation of the expected values for an independence test, right? So for example, like let's say we wanted to do the calculation for the major nonconformity in vendor B. We're going to use this row total. We are going to use this column total, and then everything gets divided by the sample size. Right? If we were going to do this calculation, we would then just use this row total, this column total, and then again, everything gets divided by the sample size. So it's that same pattern throughout the calculations of the expected values. You're just basically comparing every row and column total that you can, and then dividing by the sample size, and that produces your expected values. All right, now, once you have the expected values, you can start the test. Now, I have summarized the information by putting the expected values in brackets next to the observed counts. You don't have to do this. This is not a requirement of the test. I have just done this here so that we can see everything together. So we have our observed counts, which were the counts that were given to us in the initial problem. And then we have the expected counts, which are in brackets here, which are what we have calculated. And again, like the goodness of fit test, we have to compute the expected values ourselves in order to check the assumptions of the test, and then to get the test statistic on step 3 of this test. Okay. All right, now, so you can see the calculation. I'm just going to borrow this here. So I'm going to take this whole thing. Okay, so I'm just going to copy and paste this because I'm going to use it on step 3. Right. But once again, once we have the expected values done, we are free to start the test. Oh, sorry. Okay, so our assumptions are exactly the same. The first assumption is that no expected value is less than 1, right? So our lowest expected value is 17.43243, which is bigger than 1. So everything is greater than 1. So we can check this off. Okay, our second expected value is that no more than 20% of the entries are less than 5. So again, we have 6 entries in the table because we have 2 times 3 combinations. 6 times 0.2 is 1.2. So what we are asking is, do we have, are no more than 1.2 of the expected frequencies less than 5? So if we had 1 expected count less than 5, that would be okay. But if we had 2 expected counts less than 5, that would not be okay. And in this data set, none of our values are less than 5 because the lowest is 17.43243. So here we can say that every expected value is greater than 5, which means that 0% of the expected values are less than 5, which means that this assumption is also met. And then the last assumption is just the SRS assumption, which is true from the description of the problem. So now we can start the test. Again, the test is independence versus lack of independence. So we would have independence between the nonconformity and vendor versus lack of independence between the nonconformity and vendor. Again, I've written those as not associated versus associated, but you're perfectly free, or it's perfectly valid rather, to write this as independent versus not independent. It means the same thing. Step 2, compute the expected value, or give the significance level, sorry. And then step 3, compute the test statistic. Okay, so again, just to reiterate, with the chi-square tests, basically what we're doing is we're just following this pattern of comparing all the pairs of observed and expected quantities. So here we would have 347 minus 319.2973 squared divided by 319.2973 plus, and then we just move to the next set. It doesn't matter what order you do this in, but if I do it in this direction, I have 190 minus 217.7027 squared divided by 217.7027 plus 35 minus 73.13514 squared divided by 75.13514 plus 88 minus 49.86486 squared divided by 49.86486. And then our last one is 36 minus 25.5657 squared divided by 25.56757 plus 7 minus 17.43243 squared divided by 17.43243. Okay, so same ideas with the goodness of fit test. It's just that, well, it's the same idea. That's the truth. We just want to make sure we're matching the right pairs together. So we don't want to be combining an expected value from a different insert in the table to the observed value at a different set of the table or a different part of the table. So you can see here that I'm working all the pairs together, and that's why I organized the expected values the way that I did on the previous slide. But as long as you can keep track of which expected value goes with which observed quantity, that's fine. So we do this calculation through, and then when we find all of these different fractions and then add them together, we get a test statistic of 65.478. Okay, so that takes us to step 4. Now, you can see here, I have the degree of freedom calculation summarized. So once again, we have number of rows minus 1 times the number of columns minus 1 from the contingency table. And you can see from the subscript that that's 3 minus 1 times 2 minus 1, which is 2 times 1, which is 2. Okay, so another difference, so the alternative and null hypotheses are different between the two chi-square tests, and the degree of freedom calculation is different between the two chi-square tests, but everything else works in the same way. Oh, sorry, and the expected value calculations are different, but everything else works in the same way. The order in which we do the test is the same. The way that we use the test statistic doesn't change regardless of the test. So all of this structural work that we've been doing is consistent. All right, so now we have our choice, so we can take a critical value approach. Right, so we're working with our chi-square curve here. Okay, so we have our right skewed curve. Our chi-square value, the critical value, is going to be on 0.05. Right, and 2 in this case. So we go to our chi-square table, right? So we have 2, 0.05, and that gives us 5.991. So the critical value for this test is 5.991. Right, and then our test statistic was some massive number, 65.478. So that's obviously going to be well inside this region. So we're going to be able to reject the null hypothesis here. Okay. All right. And then here, if we take the p-value approach, right? So we're going to mark down our test statistic, which is 65.478, right? The p-value is going to be the probability that the chi-square value exceeds this quantity. Okay. So now we're going to go back to our chi-square table. We're working on 2 degrees of freedom here, right? So we're looking for 65.478. Okay, so we are obviously going to get onto page 2 because as we scroll across page 1, we're bigger than everything listed here. We move over to page 2. Okay, we're scrolling across the 2 degree of freedom line, and we're actually bigger than everything listed here as well. Right, so we have a test statistics that's larger than the largest value listed on this line, which means that the area that we want is going to be smaller than the smallest value given in the subscript here. So we would have, since the probability of interest is less than 0.005, then the p-value is less than 0.005, right? And if the p-value is less than 0.005, then that p-value is obviously less than 0.05. And as a result, we are able to reject the null hypothesis. All right. Okay, and that brings us to the end of the goodness of fit test material. So in summary, we looked at 2 chi-square tests, the goodness of fit test. Sorry, that brings us to the end of the independence test material. There's a bit of a lag on my screen, so I got distracted by that. So we've now seen the 2 chi-square tests. Again, essentially what you're looking out for here is how many qualitative variables do you have? You're either going to have 1 or 2 in this section. If you have 1 qualitative variable and you're being asked about the distribution of that variable, it has to be goodness of fit. If you have 2 qualitative variables and you're being asked about the relationship between them, it has to be an independence test. So these 2 chi-square tests work in exactly the same way, except they have different hypotheses, different expected value calculations, and different degrees of freedom. Otherwise, they're identical in their structure.